Hello and welcome to session 7 of the class on the theory and applications of network coding. In this session we will talk about finite fields as well as the requirements on the size of the finite fields imposed by different classes of network coding problems. Before we proceed, I just wanted to remind the definition of an Abelian or commutative groups. So an Abelian group is a set of elements A together with as operations that together satisfy those axioms. So just for clarity, I will refer to this operation as plus or as addition. I will denote it by plus, but it can be any other operation, doesn't necessarily be a normal addition. So, and also for convenience, I depicted here as a set of A elements. So the first axiom is closure. So if I take any two elements of the group, I can add them together, so perform addition operation A plus B. The result will also belong to the group. So we'll say that this group is closed under this operation. The second axiom is called associativity, and this basically means that order of operation is not important. So if I want to add A and B and C, so it doesn't matter in which order I perform operation. I can add A plus B together and then add C, or I can add B and C together and add A. I will get the same result. The third axiom is an existence of an identity element E, and this axiom says that we have a special element E that we can add to any other element in the group and we'll get exactly the same, right? So E plus A is equal to A, or A plus E is equal also to A. So this element, if added to any element of the group, doesn't change the value of this element. We'll get the same thing. Also, for each element of the group, the third axiom, we have an inverse. So for example, if we take an element A, there exists another element B such that A plus B is equal to an identity element. So this will be inverse with respect to addition. And final axiom is commutativity property, and this is why it makes the Abelian or commutative group, that order of operations is not important, right? So order of elements is not important, so A plus B is equal to B plus A. An example of such group, and of course in this class, since we want to be more practical, we will consider finite groups. This can be, for example, group of set can be, for example, 3 elements 1, 2, and 3, and the plus operation can be addition modulo 3. So in this case, you can verify that we have, in this case, the identity element will be 0. So added to any other element will doesn't change its value. Also, it's closed. Since we have an operation modulo 3, it will close under this addition. So for example, it's 1 plus 2 is equal to 0. And also, we'll see that any other axioms are satisfied. And for example, we have for each element, we have inverse element. So 2 will be inverse of 1 and 1 will be inverse of 2. Additional group we can consider, for example, numbers, so 1, 2, 3, and 4, and then we can consider multiplication, so regular multiplication, but modulo 5. This will be our plus operation. So we'll also see that all axioms are satisfied. So we'll have, for any 2 elements, the result will be in the group. And we'll have identity element, in this case E is 1, and for each element we'll have an inverse. For example, 2 will be inverse of 3 because 2 times 3 will be 1, because 2 times 3 is 6, so modulo 5 it will be equal to 1. So we'll have inverse for each such element in the group. We are ready now to discuss the notion of a field. A field will have 2 operations. We'll call one operation which is a plus operation or additive operation. Another operation is a dot operation, which is a multiplicative operations. So the field will be including 2 parts. One is element which we call element 0, and the rest of the group which we denote by f prime. So the requirement is that the entire group F forms an Abelian commutative group under an addition operation. So we'll satisfy all requirements that we just discussed, with 0 being an identity element. And then f prime, which is the rest of it's a group excluding 0, will form an Abelian group under another operation dot. And in addition, multiplication by any element by 0 will yield 0. And an additional requirement that those operations will satisfy the distributive law, regular distributive law. So if we'll have a plus b multiplied by c, we can get it by just taking a multiplying by c and b multiplying by c, and then adding them together, we'll have the same result as depicted here. In general, a field can include infinite number of elements. However, to be applicable to practical settings, we'll consider fields that are finite, so including only a finite number of operations, and they will be will be referred to as Galois fields. So in Galois fields, for example, GF3 will have 3 elements, so it will be 0, 1, 2, 0, 1, and 2. And addition will be regular addition modulo 3, and multiplication will be regular multiplication also modulo 3. So we'll see that it basically satisfies those two requirements. The first group, entire field, is an Abelian group under operation plus, with 0 being an identity, and the remainder of the field f prime will be Abelian group under multiplication operation dot, and also of course a distributive property is satisfied. So we'll see that for every prime number, if we have any prime number q, the Galois field with this q elements will be filled. So for example, suppose we have a GF7, so we'll write 7, 1, 2, 3, 4, 5, and 6. So in this case, it will be having 7 elements. The entire group again is a additive group with under operation plus, with 0 being an identity element. So this will be an identity element, and the rest of the group from 1 to 6 will be a multiplicative group, which is Abelian group under a dot operation, with 1 being an identity element for this multiplicative group, and of course the distributive rule will be satisfied in this case. Let us talk a little bit more about Galois field, because they are so fundamental for the theory of network coding and also traditional channel coding. So again, a Galois field is a field with a finite number of elements. So let's denote q by number of elements. And those Galois fields exist for any q which is a power of prime number. That is, we can represent q as a p to the m, where p is a prime number and m is a positive integer. Galois fields can be of two types. So one is we called prime fields, and prime fields correspond to the case where p is a prime number. So if it's, for example, GF7 will be a prime field, or GF13 will be a prime field, so any field in which p is a prime number. So such fields can be constructed using addition or multiplication rules modulo p. So basically it's kind of, we can use traditional additional multiplication modulo this prime number, and they will have exactly the number of elements as this prime number. In addition, we can construct extension fields. So extension fields will have a number of elements which is a power of a prime, so p to the m, so where p is a prime and m is strictly greater than 1. So those fields can be constructed using the notion of reducible polynomial. Unfortunately, it will be out of scope of this course to describe how those fields are constructed, but you can check it in any good book on finite fields. And for those fields, we refer to phi as a characteristic of this field. If field includes a power of primes element, we'll refer to the p as a characteristic of this field. So now let's consider a basic field which is called GF2, a Galois field with 2 elements, GF2. So in this case, the field will include just 0 and 1, and operation addition and multiplication are defined using traditional additional multiplication modulo 2. So addition will be more like XOR operation, which is modulo 2, so 0 plus 0 is 0, 0 plus 1 is 1, and so forth, 1 plus 1 is 0, and multiplication will be traditional multiplication. So this is first basic field. And so for extension fields, the rules are different from traditional addition and multiplication operation. For example, if you consider GF4, which is extension field of 2, so GF2 to the 2, in this case p is equal to 2 and m is equal to 2, we see that this field is constructed using those additional multiplication operations as specified in those two tables, and we'll see that they're very different from regular additional multiplication operations, so they cannot be constructed as prime fields using traditional operation modulo some prime numbers. So for example, here this field includes 4 elements, 0, 1, a, and b, and those operations are, for example, according to this table. So a plus 0 will get b, and so forth. So we see also in this field that any element, if we add it to its element itself, like a plus a, will get 0. So every element is inverse in additive inverse of itself. And here we also the second table depicts the multiplication operation. So in this operation we'll see that a times any element times 1 will be equal to element itself, and a times a, for example, is equal to b, and so forth. So we'll not again describing in this course how this is constructed, but the point I want to emphasize that the extension fields are built using different rules than traditional addition and multiplication operation. To summarize, Galois field exists for any p and m, where p is a prime number and m is a positive integer, and also those fields are unique. So it doesn't matter how you construct a Galois field with the same number of elements, those fields will be isomorphic to each other. For practical purposes, we are interested in a field with characteristic 2. That means that field that include 2 to the m elements, where m is an integer greater or equal to 1. And for those fields, they're interesting because they can be represented by a binary vector of length m, because they include exactly 2 to the m elements. So I can just represent each element in this field as a sequence of zeros and 1 of length m. So some of the facts about those fields with characteristic to the m that make them useful. So first of all, if I represent each element as a binary vector in certain way, then addition corresponds to bit by bit exclusive OR operation. So if I want to add 2 elements on this group and each element is represented by this binary vector, I can just efficiently perform a bitwise exclusive OR operation and obtain the result. So I can do it in linear time. An additional interesting property, as we already mentioned, that each element is an additive inverse of itself. So if you take any element b in this field, b plus b will be equal to 0. Let us proceed to the second part of the session, in which we'll talk about importance of field size, why we need field to be of a certain size. So let's first consider the simple multicast network in which we have a source node and we have 3 terminals, T1 to T3, and we have 3 intermediate nodes. And again, we want to send data. In this case, we can transmit at rate 2 from the source to all terminals. As I can see here, there exists an encoding scheme which is very, very simple. So for example, we're sending packet A over this link, B over this link, and A XOR B over this link. And there is very minimal requirements on the packet size. Actually, the packet B can just be 1 bit. So if A and B just belong to 0, 1, and then we can just perform operations over this bit and be able to deliver this packet. So it's really, we don't require packets to be a particular size to implement the scheme. Of course, in practice, packets will be much longer, but we can perform bitwise exclusive OR operation. So let us consider another example for which the field of size 2 will no longer be sufficient. So consider this network in which we have a source node S, and we have a set of intermediate nodes, and we have 6 terminals, such that for each subset of size 2 of intermediate nodes will be a terminal which will be connected to this set, for example, here. So let's try to find a solution over GF2, and we see that we quickly run into a problem, right? Because if we have 2 packets, so we want again in this network to deliver 2 packets A and B to all terminals, because min cut of this network is equal to 2. So what vectors that we can construct over a field of size 2? So in general, we see we can construct A, we can construct B, and we can construct A plus B. But we will not be able to construct any other vector, so we also can construct vector 0, but of course this will not be useful because it doesn't convey any useful information to the receiver. So if you're trying to assign those vectors to outcoming edges of node B, so we can use, for example, A for this link, B for this link, and A plus B for this link. So we have run into trouble if assigning vector for the link number 4. And this is because we cannot consider too many combinations over such a small field. We can also represent it as a matrix, the requirement for this code. So this matrix must be 4 by 2 because each row of this matrix corresponds to a particular link between the source node and one of the intermediate nodes of the network, and 2 because we have 2 packets. So the requirements imposed by this network is any 2 rows of this matrix must be linearly independent, because for each 2 rows will correspond to 2 intermediate nodes, and there will be terminals that will connect it to those 2 intermediate nodes. So our problem is again to construct such a matrix that we have 4 rows and any 2 of those rows needs to be linearly independent, and we cannot do it because we only have 3 vectors, and any other vector that we can use for row number 4 will be linearly dependent on those 2. This implies that it's impossible to construct a network code for this network over a field of size 2. However, it's possible to construct a code if we use a slightly larger field. So for example, here if we move from GF2 to GF4 and we just consider each packet is 2 bits and all operations will be performed over a field of size 4 using those tables that we discussed before. Now we can see that we can transmit, for example, packet A on this link, B on this link, A plus B on this link, and on this link, on the final link, we can transmit packet which is A plus A, big A times B, where big A is just a coefficient, just a constant that we multiply packet B and then add packet A, and that is what we will be transmitting on this first link. Now if you put it into matrix form, we'll see that the resulting matrix, again each row of this matrix will correspond to one of the outgoing links of the source node. This matrix will satisfy this constraint that every 2 rows of this matrix will be linearly independent, right? So for example, if we consider those 2 and we get a matrix which is 1, 1, 1A, and we're trying to compute a determinant of this matrix. So determinant of this matrix will be equal to 1 times A minus 1 times 1, which is equal to A minus 1. And we see that A minus 1 will be equal to B. So it will not be 0. It is important to emphasize that size of the field doesn't affect the throughput of this network. So suppose that each link can transmit 1 bit per time unit. So our goal is to transmit, the capacity of this network is 2, so our goal is to transmit 2 bits over each time unit. So in our case, if we're working on GF2, each message will include 2 bits because we have 4 elements in this field, so each message will include 2 elements. So to transmit each message, we will need 2 time units to transmit each message over each link. However, in those 2 times units, after completion of those 2 time units, the source will be able to decode 2 messages. So in total, it will be able to decode 4 bits because each message is 2 bits. So the average throughput is still 2 bits per time unit. So working over a larger field will not affect the throughput of this network. However, it's still important to minimize the size of the field because a larger field will result in a larger complexity of the operations. For example, dot operations will be much more complicated if the field is larger. You can see that multiplying 2 bits in GF2 is much less complicated than multiplying 4 bits in GF4. So it will require more computational complexity, or we'll need a larger lookup table if we'll use lookup table, so it will have a larger memory requirements. In addition, in practical implementations, the size of the field is important to minimize the overhead associated with telling the destination what kind of combination is being sent. We will talk about this later when we talk about practical implementations of network coding scheme. Just to summarize why we need field of large size, because as large as the field, the more independent linear combination we can produce. So the number of independent linear combinations will depend on the size of the field. So for example, consider the case of h equal to 2. In this case, we have 2 packets. So suppose we have packets A and packet B. And suppose we have a field of size q. So let us denote elements of this field as 0, 1, and then A, B, C, and so forth. So suppose we have this field, and let us count how many independent linear combinations we can produce. So any linear combination can be written as C1 times A plus C2 times B, where C1 and C2 are some coefficients from this field. So the first, we note that both C1 and C2, they cannot be both equal to 0. Because if they're both equal to 0, then the packet is identically equal to 0, so it's not really useful for us, right? So it will not be useful for transmitting any information. So now let us consider the case of which C1 is equal to 0. In this case, the only independent linear combination is B. So this corresponds to C2 is equal to 0. C2 is equal to 1, because any other combination, for example, big A times B or big B times B, all those will be dependent on B, so they can be excluded. So then let's consider the case in which C1 is not equal to 0. We note in this case we can assume without loss of generality that C1 is equal to 1. Because any linear combination which formed by C1 is not 0, we can find a corresponding dependent combination in which C1 is equal to 1 by just dividing it by C1. So it's enough to just assume that C1 is equal to 1. So the combinations will be A. So for example, in this case, is a combination that corresponds to C2 equal to 0. Then we have A plus B. Right, in this case, C2 is equal to 1, A plus A times B, and so forth. So all those combinations will be independent. Any two of them will be linearly independent. So for C1 is equal to 1, any other choice of C2 will yield an independent combination. Right? So the total number of combinations is equal to Q plus 1. So we see that in this case, the number of combinations will depend on the size of the queue. This is why we normally want to work with larger queues that allows us more flexibility in selecting a code. However, as we already mentioned, this will result in certain overhead.